Okay, in this video we're looking at log laws and equations. Okay, so to start off, just a little bit of terminology. So we've got our base number here, which is our 10, okay, and our exponent or index is our 2. Okay, or if we're looking here, we could have our base of e and our exponent or our index of x will go equaling y. Okay. Similarly with our logarithms, our base is our number that's just after our log that's down a little bit lower. Okay. And our exponent or index is actually what it's equal to. Okay. Similarly here, our base would be e, and our exponent or index would be x. Okay. Exponentials and logs are inverses of each other. Okay, and you can see that from our graphs. Okay, if we have the line y equals x, okay, and we have a log, well, it goes like that, and if we have an exponential, it goes like that. So you see that they're inverses to each other. E is called Euler's number, okay, and Euler's number E is just used for a lot of our real world examples because it models things in nature very well. Okay, and so we have log to the base e of x is called the natural log, and it's the ln button on your calculator, or log to the base 10 of x is the log button on your calculator. And there is probably a button on your calculator that will be something like this, okay, where we've got log and then you've got a square for your base and square for your other number. Okay, that's just allowing you to do any bases you like. Okay, so we'll talk about the index laws and our log laws. The index laws will be covered in a little bit more detail later on, but I just thought I'd put them in here as well. Okay, but we'll talk more at the moment about our log laws. So log to the base a of m plus log to the base a of n, and then that's the same as log to the base a of m times n. So if we're adding logs together with the same base, then we add these two numbers. Okay, if we're subtracting logs with the same base, okay, then we divide these two numbers. So we have log to the base a of m minus log to the base a of n gives us log to the base a of m on n. Also, and this one's a really useful one to use at times, if we have log to the base a of m to the power of n, then that's equal to n times log to the base a of m. So basically we just, whatever our power is up here, can come out the front. Okay, and vice versa. Okay, log to the base a of 1, so anytime we have a log with 1 in it, then it's just 0. Okay, log to the base a of 0 is actually undefined. Okay, we can't get that at all. Okay, and if we have log to, so a to the power of log to the base a of m equals m. Okay, and I did forget one on here. Okay, I'll talk about this one in a second. But we have log to the base a of a equals 1. Okay, so if we take a log with the base and the number in here the same, then it's going to equal 1. Okay, this one here is actually called our change of base rule. Change of base rule. Okay, so if we've got log to the base a of m, we can write that as log to the base b of m over log to the base b of a. So basically, we're using some other log, okay, and it could be something that we like 10 or e or something, okay, to transform this one. So we'll have a look at a few worked examples now. I've got a few in here. Okay, so we're going to look at simplifying log to the base 4 of 64 plus log to the base 4 of 16, take log to the base 4 of 56. Okay, the good thing about this question, okay, and what you can see here is all of our numbers here, okay, are actually powers of 4. Okay, and what we want to do is actually change them into our powers of 4. Okay, so what we can do is say, well, we've got log to the base 4 of 4 cubed plus log to the base 4 of 4 squared minus log to the base 4 of 4 to the 4. Okay, and the reason why we do that is we now take our powers out the front and say that we have 4 log to the base 4 of 4 plus 2 log to the base 4 of 4. Oh, sorry, that should be a 3 there, sorry. Take 4 log to the base 4 of 4. Okay, and we can use our log laws that says if we take a log with a base that's the same number as there, that's equal to 1. So we can just say that this is 3 plus 2 take 4, okay, which means we now equal 1. Now you could have gone through and you would have been able to get the same answer here and said, well hang on, when we've got bases the same in a plus, well we multiply these together. We could have said that we had log to the base 4 of 64 times 16, take log to the base 4 of 256. Okay, and then we can use our log law again that says when we're subtracting we're going to divide these two things. Say that we've got log to the base 4 of 64 times 16 over 256. Okay, and that would equal log to the base 4 of 4, which again is our 1. Okay, so there's two different ways we could have done that one. Okay, we'll look at this one now. We've got simplify log to the base 3 of 7 minus log to 2 log to the base 3 of 21. So what we're going to do with this one is we're going to bring our powers back up this time and say that we've got log to the base 3 of 7 squared, 8 minus log to the base 3 of 21 squared. Okay, and say that we've got log to the base 3 of 7 squared over 21 squared. Okay, and the reason why we're doing that is so that we can bring this power out and say that we've got log to the base 3 of 7 on 21 squared. Okay, we can bring the 2 down the front. Log to the base 3. Okay, 7 over 21 is 1 on 3. Okay, and we can keep working here and say, well that's the same as 2 log to the base 3 of 3 to the power of negative 1. Okay, which turns out we can also bring our negative 1 out the front to get negative 2 log to the base 3 of 3. Okay, and we know that log to the base 3 of 3 is going to be 1 because they're the same numbers. So that's going to equal negative 2. Alright, we'll keep going with some of our equations here. Okay, so we've got log to the base 4 of 64 equals x. Okay, now this one, okay, what we need to do is we need to do some rearranging here. Now, I like to call this the loopy method, and you can call it whatever you like, really. Okay, and the reason why I call it the loopy method is because we form a loop. Because we say 4 to the power of x will equal 64. So we go 4 to the power of x equals 64. And then we think, okay, well we can turn 64 into a power of 4 and say, well that's 4 cubed. Okay, therefore, okay, x has to equal 3. Now if we look here, okay, so we've done our loop around this way. If we look here, we do the same thing with exponentials. So we've got 4 to the power of x equals 64. Well, we can do our looping method again and go, well, log to the base 4 of 64 will give us x. So we get back to what we started with. Okay, and we just forming this loop around. We've got a couple more examples coming up where we need to do that. Okay, but we'll have a look at this worked example now. Okay, we've got to solve log to the base 2 of 3x plus 3 equals log to the base 2 of x minus 2. Okay, so what we're going to do with this one to start off with is do something with our 3. Okay, so we've got log to the base 2 of 3x. Okay, I'm going to say that's plus 3 log to the base 2 of 2. Okay, so I'm utilising that fact that this is equal to 1 to bring it back, this 3 back in so it's in terms of a log. And of course that's going to equal log to the base 2 of x minus 2. Okay, and we can bring this 3 up now and so we've got log to the base 2 of 3x plus log to the base 2 of 2 cubed now equals log to the base 2 of x minus 2. Okay, now we can bring these things together and multiply them. Okay, so we'll have log to the base 2 of 3x, okay, and 2 to the power of 3 is 8, so times that by 8 equals log to the base 2 of x, take 2. Okay, so what we can do is when we've got a log on both sides like this, we can equate what's in here. Okay, we equate these parts. So say that 3x times 8, well that's going to be 24x is equal to x minus 2. Okay, and then we can take our x away here and get 23x equals minus 2, so x equals minus 2 over 23. Okay. Now go look at solving this one now, and this is basically because I want to look at using our powers a bit more here, or sorry, our looping method a little bit more. Okay, so for this one, okay, well, we're going to do our looping method again and say, well, 2 to the power of 3 equals x. And then say 2 to the power of 3 equals x. To the power of 3 is 8. So x has to equal 8. Okay, that's all it is for that one. Not much work at all. Okay, I'll just find this one I want to do. Okay, so this one we've got log to the base e, okay, of x to the 4 equals negative 16. Okay, so we're going to do a little bit of work. First, we're going to bring the 4 out the front. So we've got 4 log to the base e of x equals minus 16. Okay, we can divide by our 4. So we've got log to the base e of x equals negative 4. Okay, and then we can say we've got, then do our looping method, e to the negative 4 equals x. And say x equals e to the negative 4, or that x equals 1 on e to the 4. So remember, Euler's number is actually a number, e is a number. Okay, so that is quite a reasonable answer. Okay, I think we've got one more here. Okay, and again we're going to use the looping method. We're going to go x to the power of negative 3 equals 1 on 125. So x to the power of negative 3 equals 1 on 125. Or that 1 on x cubed equals 1 on 125. Okay, so look here and we can equate our denominators now. So the x cubed equals 125. So x equals the cube root of 125. So x equals 5. Okay, so I did a couple of extra work examples that aren't from the textbook, namely these few with the looping method towards the end. It's just a really good method to use. Okay, you can do it in a more complicated way, but I just find this is really easy. It's just a nice little looping method, so use that whenever you can.